So our assignment today is 872B, which is 15 to 37 all. So we're going to take a couple days to work on this because these can be a little bit difficult. So let's say I had a fraction whose denominator was x squared minus 4, and x squared plus 9. How many unique factors does this have? So this is 2 copies of x. This is x minus 2 and x plus 2. And then I have x squared plus 9, which does not factor. So the bottom has 4 unique factors, even though its degree is 2, 3, 4, 5, 6. So the degree of the denominator is 6. But if I were to graph just the denominator, I have 4 roots. 0, negative 2, positive 2, and then plus or minus 3i. Well, but this doesn't factor, so that is an irreducible quadratic. So anytime you're doing partial fraction decompositions, you look at the unique factors, and every one of those unique factors gets its own partial fraction, its own denominator. But if any of those linear factors show up more than once, you have to list it and the square of it. So we need to do a over x plus, so I took care of this, but I also have a squared copy, so it would be b over x squared plus c over x minus 2, takes care of this one, and then d over x plus 2, and then this is a quadratic, irreducible quadratic, so it's x squared plus 9, but the numerator has to be 1 degree less. So if the bottom is quadratic, then the numerator needs to be linear. So ex plus f. Yeah. Yes, it's always addition. Yeah, because some of them actually might be negative. So it might be a over x minus b over x squared, but the b will end up being negative. So we just put them all as plus, and then some of them will change to negatives once we get there. Okay, now I don't think we're going to be doing any that are that large. That's going to be a really big system of equations to solve. So we'll start with something simple. And you don't want to just make these up because they end up being really awful. So we're going to use the examples in the book. So let's start with example 1 on page 865. Well, we're going to spend a couple days on it, so I want to do, let's do the easy ones first. All right, so 5x plus 13 over x squared plus 4x minus 5. So I need to factor the denominator. If it factors, does it? It does. So x minus 5, no, plus 5, and x minus 1. Okay? So there are 2 unique factors. None of them are squared. So this ends up being not too bad. So I'm going to have 2 partial fractions. The first partial fraction would be x plus 5, and the second one would be x minus 1. And then they're both linear, so they both have constants a or b. And again, if you did this in a different order, your a and my a will be different, but we're going to end up with the same numbers. And the a's are all going to disappear in the end, so it doesn't matter what order you perform these in. Okay, so essentially it's saying some addition with x plus 5 in the denominator and x minus 1 in the denominator will combine to create a common denominator of x squared plus 4x minus 5, and the numerator will be 5x plus 13. Okay? So we just need to figure out what number for A and what number for B makes that true. So if you look on 865, it says, factor the denominator, we did that. Then it says multiply the two sides of the equation by the least common, is that denominator, LCD? I've never seen that before. So what we want to do, we want to eliminate all of the denominators. So we do that by multiplying by this. So x plus 5 times x minus 1. And if I do that on the other side, x plus 5 times x minus 1, this cancels that. And then over here, x minus 5 times x minus 1. This cancels that. And I'm left with a times x minus 1 plus b times x minus 5. What about the left side? Do I want to multiply that together? Ooh, no. Definitely not. This cancels this, and that cancels that, and I'm left with 5x plus 13 equals all of that. Do you understand the idea behind it? So we want to get rid of all the denominators. Okay? So we pick the denominator that's bigger than all the others, which is essentially your original denominator. Multiply everything by that original denominator. And that has the effect of canceling all of these, and it's also going to get rid of all the denominators on the other side, but each partial fraction only kills a small portion of that denominator. So this got rid of that, and this got rid of that, and essentially we can make this a little bit easier. We just multiply A by what it doesn't already have. And we multiply B by what it doesn't already have, and then I don't even need to worry about the left side. Does that make sense? My common denominator is x plus 5 and x minus 1. The A partial fraction already has an x plus 5, so let's just multiply it by x minus 1. And we don't even need to write all this out, because we know it's going to cancel every time. And then over here, the B partial fraction already has an x minus 1, so it needs an x plus 5. And that gives me my original numerator, 5x plus 13, equals A copies of x minus 1 and B copies of x minus 5. Plus 5. Thank you. All right. So now 5x plus 13 equals, I'm going to distribute ax minus a and distribute bx plus 5b. Or b, sorry. All right. Now what? So it looks like we've made it much more difficult. And we're going to do kind of something sneaky that we've never done before. We have a 5x, and we have an ax and a bx. So I'm going to reorder this into ax plus bx has to be equivalent to 5x, right? There is no way for this piece or this piece to influence that, right? The x pieces are the only things that can influence the x pieces, and the non-x pieces are the only thing that can influence the non-x pieces. So I could write another equation that is negative a plus 5b is equal to 13. Okay? Now, in that green equation, do the x's matter? No, I can get rid of them. So I can just go ahead and cross this off. And now what do I have? I have a two-variable, two-equation linear system. So type that into your matrix. You could use substitution, but eventually, when these get longer, we're going to have A's and B's and C's and D's and E's. So yeah, that would work if you want. So we go into matrix, edit. How big is this matrix? 2 by 3. So 1, 1, 5, negative 1, 5, 13. Then I exit out, go into matrix math, and go down until I find RREF. REF will be incomplete, but RREF will give us the answer we want. And then we go matrix, names. So I end up with this. Hopefully you can see that. So that tells me that A is 2 and B is 3. So I need to go back to my original equation, right? My original partial fraction right here. So I have A over x plus 5 plus B over x minus 1. And I know that A equals 2 and B equals 3. So the partial fraction is 2 over x plus 5 plus 3 over x minus 1. Now, if you did the common denominator trick, you found the common denominators, added the numerators together, you would get the original fraction. So all we've done is taken the combined fraction and decomposed it into its partial fractions. Now, this is not the only answer. There are an infinite number of answers, because there may have been factors that canceled somewhere along the way, right? So how many ways are there to add fractions and get 3/4? An infinite number. But if you know what the denominators are, if you know that the denominators are 2 and 4, then one of the options would be 1/4 plus 1/2. There are an infinite number of possibilities, but that's one of them. And it ends up being the most simple version. So this is the most simple version to create the fraction that was in the original problem. Okay? All right. Let's do example 2. So example 2 is negative 3x squared plus 13x minus 12. And it's over x to the third minus 4x squared plus 4x. If you end up with a numerator that's really nasty, go ahead and graph it, find the roots, turn the roots into factors, and then you could use synthetic division or long division to figure out what they are. But in this one, it's actually pretty easy. All I have to do is pull out an x. So I end up with x times x squared minus 4x plus 4, which is x times x minus 2 and x minus 2. So it's actually x minus 2 squared. So now I have two unique linear factors. How many partial fractions am I going to have? 3. So my first partial fraction is the x. So a over x plus b over x minus 2 and c over x minus 2 squared. Okay? And here's where it gets not so fun. So we're going to multiply by that. Now, to save ourselves some time, on the right side, we know it's going to cancel. So I'm going to put this here, and that's going to cancel that. On the right side, you just multiply each partial fraction by the common denominator according to what it doesn't already have. So my first partial fraction is x. So I multiply it by everything except x. Now, do I want to re-multiply x minus 2? I already know what it is. It's right here. So the a gets x squared minus 4x plus 4. Everybody okay with that? Okay. The b term has x minus 2. What does it not have? X and the other copy of x minus 2. So it needs an x and an x minus 2, which is x squared minus 2x. So the b term gets x squared minus 2x. Does anybody not understand that? Essentially, I'm using all three of these, but I canceled one of the x minus 2's. And then what does the last partial fraction need? Just an x. So my original numerator is negative 3x squared plus 13x minus 12, and that's going to equal ax squared minus 4ax plus 4a plus bx squared minus 2bx plus cx. Now, when you get good at this, you won't have to do the step that I'm about to do, but we're not good at it yet. So I need to link all of the x squareds together. So I have ax squared plus bx squared. What about the c's? There is no cx squared, which means in my calculator, there's going to be a 0, a placeholder, and that is equal to negative 3x squared. And then I link all of the x's together, and there happens to be an x for each of the variables. So, negative 4ax minus 2bx plus cx equals 13x. And then for my constants, I have an a constant, but I don't have a b or a c constant. So it's going to be 4a equals negative 12. Now this one wouldn't be too hard to figure through. We know a is negative 3. And again, you can go through and you can get rid of all the x's. They no longer matter. Or you, instead of doing it by hand, and this one really isn't hard to do by hand, you just go into your matrix, do a 3 by 4, type in all the numbers, which is what I'm going to do. So define your matrix as a 3 by 4. And anywhere there's not a letter, you need to put a 0. And then exit out and do your reduced row echelon form. And I get A is negative 3, B is 0, and C is 1. Okay, so then I go back to my partial fractions, and I replace these with the answers, which were, I don't remember. So negative 3, this is a 0, which means it didn't even happen. We can get rid of it. And then 1. So negative 3 over x plus 1 over x minus 2 squared is equal to the original fraction. Is that so much fun? Okay, I think the next one's going to have a quadratic in it. All right, so Okay, we're going to skip example 3. It's the same basic idea, just a little bit. Maybe not. Nope, let's do example 4. Yeah. Well, yeah, but we need to do one where it has like ax plus b. You haven't seen that one yet. So example 4, 7x squared plus 2 over 2x plus 1 and x squared plus 1. Does the denominator factor? No. How many unique factors are there? Just 2. One of them is linear, and one of them is quadratic. So how many partial fractions will there be? Just 2. Which is kind of confusing because sometimes when you have x squared, you end up with 2 partial fractions, and sometimes you only have 1. And if you can remember when you do each one, then the rest is just long. It's not difficult. So a over my first factor, 2x plus 1. And then my second factor is x squared plus 1. But what's the numerator going to be? bx plus c, because it's an irreducible quadratic. So my numerator has to be 1 degree less than the irreducible portion, so bx plus c. And again, if you reorder these, it doesn't matter. When you do your reduced row echelon form, your answers will just be in a different order. Okay? So this partial fraction needs that version, x squared plus 1. And then here's where it gets a little bit messy. This one already has x squared plus 1, so we multiply by 2x plus 1. And you can see the bigger your denominator is, the messier it's going to be. If we had another, let's say, x squared plus 2x plus 4 over here, then we would have to take that and multiply it to both of those, and it gets really, really awful. But we don't, so let's not worry about it. So 7x plus 2, and again, each of those are going to cancel when I bring in those. 7x squared plus 2. So that's ax squared plus a, and then I have to distribute all of that, which is 2bx squared plus bx plus 2cx plus c. And now the original numerator is missing the x term. So if I go through all the x squared terms, there's an x squared, there's an x squared, there's an x squared, and there is no c. So ax squared plus 2bx squared plus no c's is equal to 7x squared. What about the next line? So I don't have an ax, so there's nothing here. And then I have a bx plus 2cx, but the numerator didn't have any x's, so that's a 0. And then for my constants, I have a 2, an a, and a c. I don't have any b's. So a, no b's, so I'm going to put a 0 there, plus c equals 2. And once you do this enough times, you might not even write all that down. And you're certainly not going to write the x squares and the x's, because they're not needed. Once I have this set up, I can go ahead and drop all the x's. So put that in my calculator. So once again, this is a 3 by 4. 1, 2, 0, 7. 0, 1, 2, 0, 1, 0, 1, 2. So my answer set is 3, 2, negative 1. So I go back to my original partial fractions. Move this out of the way. So A is the number 3, and then B is 2, and C is -1. So 2x minus 1 over x squared plus 1. Does that make sense? Okay, now we're certainly not going to do all these today, so so we're going to start with 15, and we're going to go all the way to 30. How far is it? 37. So maybe just try to finish the 872 today. You might not get all the way done. So just start on 15, but you don't need to go past 23 or 24. And then the question is, are any of them improper? No. None of those on the first page are improper. Are any of them on the second page improper? No, I don't see any. Okay. Good luck.